Hi everybody, in this video we are going to be talking about 18.1.1, Introduction to Exponential Functions. So first what we're going to do is we're going to put our definition in here. So exponential functions typically have the form of f of x equals b to the x, where x is any real number and b is going to be greater than 0 and b cannot equal 1. So I guess I want you to think about for a moment, because this is our think question here, why do we have the restrictions for b has to be greater than 0 and b cannot equal 1? So I want you to kind of like pause the video and think about, why do we have to have those restrictions of b has got to be greater than 0 and b cannot equal 1? And what you can do is you can kind of think about, well, what's going to happen if, for example, let's say that we had a function of x that was maybe -2 raised to the x power. And so if b is less than 0, or yeah, if it's less than 0. So if we had that situation and then we just started plugging in values and we had 1, and then if we did like -2 squared and -2 to the third and -2 to the fourth, what I'm hoping you're remembering is that here we would get -2, here we would get a +4, here we would get a -8, and here we would get a +16. And so what that means on our graph, graphically, is that, as we're increasing 1, 2, 3, 4, the first one, it would be down here at -2, and then the next one would bump here up at 4, and then the next one would come down here at 8, and then the next one over here would come way up here to 16. And so that's not an exponential curve at all. It's bouncing back and forth across our x-axis. So it's not going to work for that. Well, why can't it equal 0? Because if we equaled 0, it's just going to be a straight line going across, right? Like 0 to the first, 0 squared, 0 to the third. It would be a straight line. Same thing with b equaling 1. If our base equaled 1, and we had like 2, not 2. If we had 1 to the first and 1 squared and 1 to the third and 1 to the fourth, well, same thing, our output's going to constantly be 1, so it would be graphing a straight horizontal line. So that is why we have those restrictions in place. So here, let's look at some other characteristics that are going to be found in our exponential functions. The domain is going to be the set of all real numbers. The range is going to be the set of all positive real numbers. The graph never touches or goes below the x-axis. So it's always going to be above the x-axis. The point 0, 1, I don't know. I don't like this word always in here. So really, I should change that. It's not really always, it's going to be most of the time. So like in our just typical graph, if we have no transformations going on in our graph, if it's just going to be like f of x equals 3 to the x, something like that, this is going to be true. 0, 1 will always be on our graph. But if we have something else going on, like if we have like a vertical shift, a horizontal shift, something like that going on, then it's going to be a little bit different on that 0, 1. So almost always, how about we do that? Will almost always be a point plotted on your graph. For exponential growth graphs, when b is greater than 1, so when b is greater than 1, as x increases, f of x grows So these are your y values, right? So as your x values, your inputs, as your inputs increase, your y values or your outputs are going to grow more quickly. So it grows more quickly. For exponential decay, this is for when our b is going to be greater than 0, but less than 1. So as x increases, f of x is going to decrease and also approach 0. So f of x decreases and approaches 0. So just kind of a sketch of our exponential growth graphs. So on here, if we are doing our exponential growth graphs, it's going to look something like this. And again, this is going to be the point 0, 1. And so it's going to look like this. It's going to come up, and then we're going to increase. And it's our exponential growth. If we are looking at exponential decay, so by the way, let's come over here. I'm going to give you an example of that. So that could be something like 2x. If we did something like f of x equals 3 to the x, so it's still, the line's going to come below my red line. It's going to cross at 0, 1, and it's going to come on the inside of that red line on the other side of 0, 1. So it's going to look like that. If we did an exponential decay, what that's going to look like instead, it's going to be kind of like this. So it's going to look like that. So let's say this one, and again, that's just a super rough sketch, but let's say that one was like 1/2 to the x. So then if we did f of x equals 1/3 to the x, that one is going to be like up like this and then come down like that. So that's going to be the difference between those, just in terms of their trends. And we're actually going to go graph those on a page coming up. And so you're going to get to see what those trend lines look more closely here in a minute, what they look like. All right, so let's look at our steps for graphing these, because we're getting ready to go graph them over here. So our graphing exponential functions, we're going to make a 4-column table, just like we did for linear equations. So we're going to make a 4-column table. And we're going to evaluate the following x values in each function. So we're always going to do this. We're going to do -2, -1, 0, 1, and 2. So we're doing those 5 values because sometimes they increase very rapidly. And so we want to see what that change is going to look like. And then we're going to go plot the ordered pairs. Tips. It's a good idea to include 0, positive, and negative values if possible. Well, we're going to do that because I'm requiring that you do all 5 of those. So we're going to end up doing that first tip. And then the second one, it says, recall if the base has a negative exponent, then you are going to take the reciprocal of the base to make the exponent positive. So that's just a reminder of your exponent rules. So for example, if you have your base of 4 raised to the -2 power, which is what you see here, in order to make it positive, we would do this next step here of doing 4/1, that's raised to the -2nd. In order to make that -2 positive, you switch these 2 up here. And so it's going to be 1/4 squared. All right, so what we're going to look at now, we're going to do our exponential growth, and we're going to make a table, and it's going to be kind of crowded on this. So we're going to kind of squeeze them in, and that's intentional. So I'm wanting you to put all 3 of these graphs. We've got f of x equals 2 to the x, 3 to the x, and 4 to the x, all on the same graph. And that's because I'm wanting you to see what the different graphs look like and how the base values here, how they affect the overall trend of your graphs. because that's what we're going to kind of note down here. So like as our base is increasing, what do we notice for the shape of our graph? And so we're going to put them all on the same grid. So it takes a little bit of time to get this all graphed up. And so just hang with me, and we're going to make tables for each of these, and then we're going to graph them, and then we're going to make our notes here. So what I want you to do first is, what I would do is get like maybe a couple different colored pens, some pencils, like some different colored pencils. Or if you don't, if all you have is like a single pencil, then you do something where like one is the solid line, one's the dashed line, and the other one's going to be the dotted line. So do something like that so that you can tell which line is which, because otherwise it's just going to look like a big mess of lines on your graph. All right, so mine, I'm going to start with red first, and my red is going to be the 2 to the x, and then I'll change up and try to remember to switch to a different color for a different function. So what we're going to do is we're going to make our table, and so it's going to be x, and then it's going to be my function of 2 to the x, and then it's going to be my y, and then my ordered pair. And then I already told you that we're going to 100% of the time, we're going to do -2, -1, 0, 1, and 2 for each of these. And so we're just going to start plugging those in. So I've got 2 raised to the -2 power. And again, you're asking yourself, how do I make that positive? It would be 1 over 2 squared, which is going to give me 1/4. And so then you're going to get -2 1/4. I totally get that it will be a little bit harder to do that -2 and 1/4. Just do the best you can. So let's put that on here. So -2 1/4. The other thing I'm going to tell you right now is that you're actually on our next 2 graphs, you're going to have 2 points that have to fit in between the point we're getting ready to draw and our x-axis. So I'm going to push mine down a little bit so it looks more like it's at -2 1/2. So -2, and then I know that looks more like 1/2, but the next 2 are going to have to go underneath that red dot. So, all right, here we go. Next one, we're going to do 2 to the -1. That's going to be 1 over 2 to the first, which is 1/2. And so then we're going to have -1 1/2. So go graph that one. So -1 1/2. Guess what? It's going to look almost like a horizontal line right there. All right, so next one, 2 to the 0. That's going to be 1 1, and that's going to be 0 1, right? There's our point, 0 1, that I said is almost always going to be on our graph. Then we're going to do 2 to the first, which is going to give us 2, and we are going to graph the point 1 2. And then we're going to do 2 to the second. That's going to give us 4, and then you're going to graph the point 2 4. So 2 4. This one, I'm going to go ahead and do 3 as well, so you can see where this one's going to go. So 2 to the third, that's going to give me 8, and that's going to be 3 8. So I'm going to go ahead and graph that one too. You can just graph the point on there, 3 8, and it's going to look like that. All right, so I'm going to go ahead and draw my graph. Make my points here. So it'll look like this. And this, and I'm going to label it too, is going to be my y, or my f of x. I should do that. F of x equals 2 to the x. All right, so now I'm going to switch up pens. I'm going to do black. Black's going to be my 3 to the x. I'm going to come down here. So we're going to squeeze this in 2. So it's going to be x, 3 to the x, y, ordered pair. You should pause the video and try to do this one on your own, and then check and see how you do on it. I'm going to go ahead and keep doing it with you. And then you can unpause the video and see how you did. So -1, 0, 1, and 2. And so this one, we've got 3 to the -2nd. That's going to be 1 over 3 squared, which is going to give us 1/9. And so then we're going to have -2 1/9. So that one's going to go just under my other one that I'd put on there. And then I'm going to have 3 to the -1st, which is going to be 1 over 3 to the 1st, which is 1, well, I already put it there. It's 1/3. And then we're going to have -1, 1/3. So -1, 1/3. And then guess what? We're going to do 3 to the 0, which is going to give us 1, 0, 1. So they're going to intersect at that point. And then we're going to have 3 to the first, which is going to give me 3. And I get the point 1, 3, and I'm going to graph that one. So that's going to go up here to 1, 3. And then I'm going to do 3 squared, which is going to give me 9. And then I'm going to go graph the point 2, 9. So 2 up here to, what is that, 9 right there? All right, so you're going to see again that my black line is on the underside of my red line for the negative x values. And then it goes on the inside of my red line or closer to the y-axis as we go into our x values that are greater than 0. All right, so this line here is going to be my f of x equals 3 to the x. I should have made these g of x and h of x, by the way. I should have done that. All right. Let's do our next one. So this one's going to be blue. I'm going to do x, and I think it was 4 to the x, right? Yep, 4 to the x gives us our y and then our ordered pair. So again, we're going to have -2, -1, 0, 1, and 2. And so here we're going to have 4 to the -2. That's going to be 1 over 4 squared, which is going to be 1/16. So we're going to have -2 and 1/16. And then because I'm going to have to shift up and down so many times to graph, I'm just going to keep filling in my table, and then I'll graph when I'm done with my table. So then I'm going to do 4 to the -1, which is going to be 1 over 4, which is going to be -1, 1/4. And then 4 to the 0, which is going to give me 1. So I'm going to graph the point 0, 1. And then 4 to the first, which gives me 4, which will give me the point 1, 4. And then I'm going to do 4 squared, which is going to give me 16, and it's going to be 216 for my points. So I am going to scroll up for a moment. I'm going to graph all those points. So my line already shifted on me when I moved down, my black line. And like I said, do the best you can. You can tell I'm doing the best I can. It's not supposed to touch your x-axis. So it'll get infinitely close to your x-axis on the left-hand side of your x. So like quadrant 2. So how about if I do this? So quadrant 2. It's never going to touch your x-axis. It's going to get infinitely close, but never touch. All right, so then it's going to touch 0, 1, and then we've got 1, 4, and then 216 is going to be way up here. So 216 is going to be about right there. So I'm just going to label that point. All right, so then we're coming in here, going to hit that blue point, and then I've really got to extend it up here like that to go up. And so this line, if I'm using my new letters here to tell what it is, it's going to be my h of x equals 4 to the x. Okay, so there are our lines, or trend lines, and I want you at this point to make some observations. So what do you notice about the different lines? And things that I want you to think about is like, for our base is greater than 1. So I'm hoping you notice that all of our bases here, this is our base, they were all greater than 1. So they're not going to be in between, 0 and 1. It's not going to be a fraction. So these are going to be trends for all of our bases that are going to be greater than 1. So here, all the graphs hit what? All graphs intersected at 0, 1. That's one thing I'm noticing. The graphs all intersect the y-axis, but never the x-axis. Other things that I'm thinking about, so as the base of B, so as our base of B increases, again, think about what that means. So that was going from like my red table to the black table to the blue table. For each of those, my base is increasing. And as X values do I really want this? Okay. And as X values, and I'm going to switch this, and for X values greater than 0, let me read my own handwriting on my paper for a minute. Greater than 0, the curve gets steeper and closer to the y-axis. All right, and then we're going to talk about that in a second when I can point to my graph. The other one I want you to write in here is as the base B increases, and for X values that are less than 0, the curve gets closer to the y-axis, or gets closer to the x-axis. The curve gets closer to the x-axis. All right, so what that's meaning is, I'm hoping you're noticing these trends. So for all the things that we talked about, so as our base is increasing, that's talking about this part. So as our base is increasing each time, so we're looking from the red to the black to the blue, you should be noticing that it gets, and again, it messed up my graph when I scrolled. So none of those should look like they're crossing the x-axis. Anyway, so for the graphs in quadrant 2 here, so as our x's are decreasing, like they're going further and further towards negative infinity, our graphs, as the base is increasing, gets closer and closer and closer to the x-axis. And that is true as the x values increase and get infinitely more positive. So as they're increasing towards positive infinity, then they're getting closer and closer to the y-axis. So they're pulling in towards the y-axis, and similarly as the x values continue to decrease and get closer and closer to negative infinity, they're getting closer and closer to the x-axis. They all cross at 0, 1, and none of them intersect the x-axis. All right. So now let's look at exponential decay. So we're going to talk about exponential decay. We're going to graph these two. So let's go ahead. We're going to make up our table again. So we're going to have f of x equals 1/2 to the x. You actually don't have to put f of x in there. I don't know why I added that in. And then you've got y and then ordered pair. All right, so then we're going to do -1, -2, -1, 0, 1, and 2. And I'm going to go ahead and I'm just going to make this one black because I already started it in black. So this one we're going to do 1/2, and I'm raising it to the -2nd power, which again, this is a reminder, to make that positive, we flip the inside, right? It's going to be 2/1 raised to the 2nd power, which is going to be 2 squared, which is going to give me 4. So then I'm going to have -2, 4 for this one. My next one's going to be 1/2. I'm raising it to the -1st power. Again, to make that positive, it's going to be 2/1 raised to the 1st, which is 2. Then I'm going to have negative 1, 2. And the next one, I'm going to have 1/2 raised to the 0, which is going to give me 1. So we're going to graph 0, 1. And then we're going to have 1/2 raised to the first, which is going to give me 1/2. And so I'm going to get 1, 1/2. And then the last one, I'm going to get 1/2. I'm raising it to the second power. That's going to be 1/4, because it's like 1/2 times 1/2. And then this is going to give me 1/4. And then I'm graphing the point to 1/4. So I'm going to go graph those. So we've got -2, 1, 2, 3, 4. And then we've got -1, 2. We've got 0, 1, 1, 1/2. Again, we're going to have, my next graph is going to go on the inside of the, like, it's going to go below that dot I just put in there. So just give yourself some space. And the other one's going to be at 2, 1/4. And I know that looks more like 1/2, but it's intentional so I can get my next line underneath it. All right, so we've got this line. It's going to look like this. And then I'm going to do a red for my g of x. So for my g of x, again, I'm going to do my x values. My g of x is going to be 1/4 raised to the x power. And then I've got y and then my ordered pair. So then we're going to do -2, -1, 0, 1, and 2. So here we're going to do 1/4 raised to the -2nd. Again, that's going to be 4/1 squared, which is going to give me 16. So it's going to be -2, 16. Then we're going to have 1/4 raised to the -1st, which is going to give me 4/1 raised to the 1st. It's going to give me 4, and then we're going to have -1, 4. Then we're going to have 1/4 raised to the 0, which is going to give me 1. So that's going to be 0, 1. 1/4 raised to the first power is going to give me 1/4. So I'm going to have 1, 1/4. And then 1/4 raised to the second is going to give me 1/16, which is going to give me 2 and 1/16. And so now we're ready to go and graph those. So -2 to -2 and then up to 16, we're going to have to extend our graph. So it's going to be up here. And then I'm just going to write that in, -2, 16. And then our next one was going to be what? -1, 4. So -1, 4. And then we've got 0, 1. And then we had 1, 1/4. And then 2, 1/16. So fill those in. So it's going to be like this a little bit. All right. So it's going to look kind of like that. Again, the red one is 1/4 raised to the x. The black one is going to be 1/2 raised to the x. And so I want you to think about like how our graphs, like what are some observations we can note? Oh, excuse me, for down here. And again, so this is going to be for our base, when our base is going to be, oops, I gotta switch that up because it's going to be a compound inequality. So when our base is going to be greater than 0 but less than 1. So that just means it's going to be a fraction. It's going to be a positive fraction in there. So first of all, guess what? The graphs still intersect at what? 0, 1. So graphs intersect at 0, 1. Graphs cross the y-axis. But not the x-axis. And then here, be careful on this one. So as our base of B decreases, so again, that means like going from the black one to the red one. So as it's decreasing, and for X values less than 0, the curve gets steeper and closer to y-axis. And then we're going to talk about the other side. So as base B increases, and for X values greater than 0, so now we're talking about what it looks like for our quadrant 1. Wait, I'm sorry, for quadrant 2. So as base increases, and for X values that are going to be greater than 0, the curve gets closer to the x-axis. All right, so let's talk about that for a second. So it says in our third bullet, it says as the base B decreases, so as it is decreasing, which means the first one we graphed, the black, it was 1/2. The red one is our 1/4, so that means our base is decreasing. And for X values that are less than 0, so X values that are less than 0, we're talking about this portion of the graph. Our graph, and again, we're talking about how the black line compares to the red line, the curve is going to get steeper and closer to the y-axis. So here, that one should have been talking about quadrant 2. And then the next one, here it says as the base B is increasing, so as our base is increasing, and for X values that are greater than 0, the curve is getting closer and closer to the x-axis on that one. So that one was talking specifically about our quadrant 1 and what's happening there. All right, so that's kind of the graphing. And again, what you're needing to pull from that is, what do the trends look like? Like, what are the trends of the graphs? They're hitting at 0, 1. They're either pulling towards one axis, like the y-axis, or the x-axis based off certain characteristics. And those are the characteristics you're going to need to know. Also, you need to recognize the general function shape. Like, this is an exponential decaying, so it's decaying exponentially. This is what the general curve looks like in these graphs. Whereas these trend lines up here in these graphs are exponentially increasing. And so kind of knowing what's happening as our trend lines, so as our base is increasing, these trend lines, each one pulls closer and closer towards the y-axis because it's increasing at a much higher rate. And so that's why. So then we are going to talk about some word problems in these next couple of examples. So we've got some word problems. It says we can apply exponential functions using the compound interest formula, which gives us A, and then it gives us our formula where P is our principal amount. A is going to be the amount of money you would have. So P is our principal amount, our initial investment. A is going to be our output, like what comes out after we've invested it. We have an interest after so many years, which is going to be our T. Using an annual interest rate, again, we're expressing our rate as a decimal. And M is going to be the compounding periods per year. So if something is compounded semi-annually, that would be 2 times a year, right? So every 6 months. So if you invest, well, and before we even do that, I want you to write out our letters off to the side, A, P, R, M, and T. And I'm just pulling those straight from our formula right here. So I just see that we have an A, a P, an R, an M, and a T. And so I want you to just write those letters in. So if you invest $1,000 in an account paying 4% interest compounded quarterly, how much money will you have after 3 years? So what are we looking for? Are we looking for the principal or the amount? And I'm hoping you're saying we're looking for the amount, because it's how much money will we have after 3 years. So this is our unknown. Our principal, how much money did we initially invest, is going to be $1,000. What's our rate? It's going to be 0.04. So the M again, don't forget what our M is. It's our compounding periods per year. It's compounded quarterly. So how many times is that per year? 4. How many years? 3. So we've got the information. Now let's plug it into our formula. So we have A equals, which is what we're looking for, our principal times 1 plus our rate, which is going to be 0.04 over our M, which is 4. And we're raising that to the 4 times 3, to the 4 times 3 power there, because it's M times T. So now this becomes somewhat of a calculator problem here. So here in our parentheses, you should be getting 1.01, and you should check, make sure that's right. Raising it to the 12th power. So in your calculator, order of operations says take care of this exponents first. Do this first, and you should get 1,000 times something that's 1.1268, and that number keeps going. So put this in your calculator, keep that number in your calculator, now multiply it by 1,000, and you should get 1,126.8250, and it keeps going. So then we're gonna estimate that, and it says, well, how much money? And we're gonna round to the hundredths place. How much money is that after 3 years? So it's gonna be $1,126.83. And again, I'm putting approximately because we did just round it. All right. So let's try this one. So same thing, we're going to use our same formula. So we've got our same variables of A, P, R, M, and T. And it says Billy's mother put $100 into a bank account for him when he was born. Okay, so that means that's our principal. The account gained interest at a rate of 3% per year. So 0.03%, because again, we're taking that 3 and you're converting it into a decimal. So it's 0.03. And it's compounded monthly. How many times is that per year? 12. Assuming no more money was deposited and none was withdrawn, how much money will be in the account when he turns 18? So how many years is that? 18. And we're looking for A. So A is going to equal our principal, which is 100, times what came next, 1, plus our rate, over our M, which is 12, and that's being raised to the 12 times 18 because it's our M times our T. So then we're going to have 100 times what ends up going in our parentheses here. So it's going to be 1.0025 raised to the 216th power. So in your calculator, order of operations would tell you to do this part next. So put that number in your calculator, and then we're going to write it out as a big long decimal, 1.71485. Don't round it. Show me that you know that that decimal keeps going. While that big long irrational number is in your calculator, multiply it by 100, and then we should be getting 171.48508 ... How much money was it? So we're going to again round to the hundredths place. Kind of sad. It's only up to $171.49 after 18 years. But again, that's because it's not a great interest rate and you only invested $100. So it's not going to be that much if nothing more is put into the bank. You know, something's better than nothing. All right, let's look at our last two examples. So we have got something we're looking at radioactive decay now and half-life. So here we've got the formula. It gives it to us right here. And it gives the remaining amount R from an initial amount that's given. And the H is going to be the half-life of the element, and T is the amount of time passed. So here we go. We're given the information. The cesium-137 is a radioactive element used in medical applications. It has a half-life of about 30 years. So there's our H. That's going to be our half-life. Suppose a laboratory has 10 grams of cesium-137. So right here, that's going to be our initial amount because it's telling us what do we have. If they don't use any of it, how much will still be the element cesium-137 in about 60 years? So because the half-life is kind of like shelf life, right? So an element has a half-life of a certain amount of time, and then it's no longer that pure element, right? So we've got our variables of R, A, T, and H. We're looking for R, so how much is going to be still cesium after 60 years? 60 is going to come here for time. How much did we start with? We started with 10 grams. This is years. Our half-life is also 30 years. By the way, if they weren't in the same unit, we'd need to put them in the same unit, right? So R is equal to 10 times 1/2 raised to the T, 60 over 30. And that's going to give us 10 times 1/2. And we're raised to the second power. So 1/2 squared is going to be 10 times 1/4, which again is going to be 10 over 4, or you can reduce here like I normally do. And I would take a 2 out, and this would be 5. So then it would be 5 halves. And then that's going to end up being 2.5 grams. So after 60 years, if nothing is used up, we'd only have 2.5 grams of cesium-137 left. That would still, like, of that element, still be considered cesium-137. All right. So now what I would like for you to do is I want you to try this one. So I want you to try this one on your own. When you're plugging it in, you should be getting R is approximately 1.3258 grams left. So try that one on your own, set it up, and see how you do. So that is it for this video. Thanks for tuning in, guys.